Hi everybody! This lesson is concerned with the mathematical expectation of a random variable. We start by defining the expectation, or mean, of a discrete random variable, state some properties of the expectation operator, and compute expectations for some common discrete distributions. We then repeat this process for continuous random variables. After that, we will consider the definition of conditional expectation and discuss some properties that will aid in its computation. We will also reconsider the notion of independence for random variables. Finally, we introduce the notion of the moments of a random variable, examples of which are the variance as well as the skewness and kurtosis, and these are important moments to consider in financial data. Let's begin by considering the definition of expectation for a discrete random variable. Let x be a discrete random variable with the property that the probability that x is equal to xi is equal to pi, for I ranging from 1 up to m. In other words, capital X takes only the values x1, x2 up to xm. Suppose now that we draw elements omega n from the sample space omega with replacement and independently a large number capital N of times. And we observe the values of the random variable x in the states omega n. We then expect to see the outcome x is equal to xi, a proportion pi of the time. In other words, we expect to see it approximately pi times n many times. Thus, if g is a function from the reals to the reals, then the average value of all the observed values of g of x is just the sum of all the observed values of g of x divided by n. Now we see g of x1 approximately p1 times n times, gx2 approximately p2 times n times, and so the sum of all the observed values of g of x is approximately equal to the numerator here. We must divide this by n, and then we obtain the following result. Now, recalling that pi is just a probability that x is equal to xi, this amounts to the following sum. And that gives us a definition. We define the mean or expectation of g of x as follows for a discrete random variable. If x is a discrete random variable with PMF given by f sub x, and if g is a function, then we define the expectation of g of x to be the sum over all possible values of the random variable capital X times the probability. In other words, it's just the sum of g of x times the probability mass function of the random variable x, summed over all possible values of the random variable capital X. In particular, if g is the identity function, i.e. g of x is equal to x, then the expectation of the random variable x is just the sum over all possible values of the random variable x of x times the probability mass function. In the same way, we can define expectations of functions of more than one random variable. Suppose that x and y are discrete random variables with a joint PMF fxy. In that case, the expected value of g of xy is just the sum over all possible values of the random variable x and the sum over all possible values of the random variable y of g of xi yj times the probability that x is equal to xi and y is equal to yj. Now this probability, of course, is just the joint probability mass function evaluated at xi and yj, and hence we obtain the following sum, where little x ranges over all possible values of the random variable capital X, and little y ranges over all possible values of the random variable capital Y. The expectation operator has the following properties. Firstly, it's easy to see that the expectation of a constant random variable is just that constant random variable. Secondly, the expectation of c times a random variable is just c times the expectation of that random variable. Thirdly, the expectation of the sum of two random variables is the sum of their expectations. Notice that the second and the third property here show that expectation is a linear operator. In other words, you can take out a constant or a scalar and you can split up a sum. To see that the expectation of the sum is equal to the sum of the expectations, note that the sum of two random variables can be considered as a function of two variables, g of xy, where g of xy is just x plus y. Thus, by definition, its expectation is the sum over all possible values of the random variable x and the sum over all possible values of the random variable y of the function g of xy multiplied by the probability mass function. Now we can split up this sum as follows. In the second term, we've also interchanged the order of summation. In other words, we're now summing over y first and then over x. If we consider this sum over here we are summing the joint mass function over all possible values of the random variable y. And if you recall, that's just equal to the marginal probability mass function of the random variable x. In other words, this sum over here is just the marginal PMF of x. In the same way, this sum here is just equal to the marginal PMF of y. Now, by definition, the first sum is the expectation of the random variable x, and the second sum is the expectation of the random variable y. Now observe that generally it's not the case that the expectation of a product is the product of the expectations. A simple counterexample here is where y is equal to x. Take, for example, a random variable x which takes only the values 1 and minus 1 with equal probability. In that case, the expected value of x is 0, and so the square here is 0. On the other hand, x squared is either 1 squared or minus 1 squared. And since both 1 squared and minus 1 squared are equal to 1, this is just the expected value of 1, which by the first property is equal to 1. And 1 is indeed not equal to 0. Let's compute the expectation of some discrete distributions. Recall that by definition, the expectation of a discrete random variable x is just the sum over all possible values of that random variable x of the product of the value times the probability of taking that value. Now, if, for example, x is Bernoulli p, then x takes just two values, namely 1 and 0. It takes the value 1 with probability p and the value 0 with probability 1 minus p, and so its expectation is p. Next, if x is binomial with parameters np, then by definition the expectation is the sum over all possible values, and in this case the values are integers from 0 up to n, of the value times the probability. Now the probability that x is equal to k is given by this expression here involving binomial coefficient, and at first glance that looks quite complicated. However, there is an easier way to compute this. Recall that if y1 up to yn are independent Bernoulli p random variables, then their sum is binomial np. And so we can use the linearity of the expectation operator to compute the expectation of x as the sum of the expectations of the yk. We've just seen that each of these expectations is equal to p, and since there are n of them, the result is n times p. Now suppose that x is Poisson distributed with rate parameter lambda. Using the definition of expectation, the expectation of x is just the sum over all possible values of the value times the probability. The probability that x is equal to k is e to the minus lambda times lambda to the k over k factorial. This k here cancels out with a factor in k factorial, leaving k minus 1 factorial. We can also take out one of these lambdas outside the summation to obtain the following result. And if we then change the variable k to j, where j is equal to k minus 1, we obtain the following. Now, this infinite series here we recognize as the Taylor series for e to the lambda, and hence the expected value of x is equal to lambda. Now recall that the Poisson distribution models a number of arrivals of independent events per unit time. We now see that we can indeed interpret lambda as a rate parameter because we expect lambda events to arrive per unit time. We now move on to the definition of expectation for continuous random variables. Let capital F sub x be the cumulative distribution function of a continuous random variable x, and let delta x be small. In that case, the probability that capital X, the random variable, lies between x and x plus delta x is the difference of the CDF evaluated at those two endpoints. By definition of the derivative of f sub x, that's just the derivative times delta x. Now recall that the derivative of the CDF is just the PDF, and so this probability here is approximately equal to the PDF times delta x. Suppose first that x takes value only in an interval from a to b. We will partition this interval into n many subintervals of length delta x. So a is x0, x1 is a plus delta x, a2 is a plus 2 times delta x, etc., and xn is b. The difference between two successive points is delta x. We now define a discrete random variable x star which is supposed to approximate x as follows. We set x star of omega to be equal to xi whenever x of omega lies between xi and xi plus 1. In other words, we look at the value of x in a particular state of the world. If we see that it lies between xi and xi plus 1, then we set x star to be equal to xi. In that case, x star is a discrete random variable because it only takes the values x0, x1 up to xn. And moreover, the difference between x and x star is always less than or equal to delta x, because when capital X lies between xi and xi plus 1, then x star is equal to xi, and the distance from capital X to x star is less than or equal to the distance from xi plus 1 to xi. Now, as delta x approaches 0, x star obviously becomes a better and better approximation of x. Observe also that the probability that x star is equal to xi is precisely the probability that capital X lies between xi and xi plus delta x. This here is just xi plus 1. And that is approximately equal to the PDF evaluated at xi times delta x. Now again, we reiterate x star is a discrete random variable, and hence we already know how to define the expectation of x star. Now for reasonable functions g of x, because x star is an approximation of x, we should have that the expectation of g of x is approximately equal to the expectation of gx star. But the expectation of g of x star is just the sum over all possible values of the values times the probabilities. And that can be written as the following sum. In the limit as delta x goes to 0, x star becomes a better and better approximation of x, and so in the limit as delta x goes to 0, we obtain our definition of the expectation of a continuous random variable. The expected value of g of x is the following limit, and this is just a limit of a Riemann sum, and hence a Riemann integral from a to b of g of x times the PDF of the random variable. Notice again that what we have here is a sum over all possible values of capital X of the values times the probabilities. Now we considered here the case where x takes only values between a and b, the case where x takes values on the entire real line, in other words from minus infinity to infinity for example, can be dealt with by letting a go to minus infinity and b to infinity. In that case we obtain the following definition. If x is a continuous random variable with PDF little f sub x, we define the expectation of g of x to be the integral from minus infinity to infinity of the product of g with the PDF. In the same way, we can define expectations for functions of more than one continuous random variable. Suppose, for example, that x and y have a joint PDF, f sub xy. In that case, we simply define the expected value of g of xy to be the double integral from minus infinity to infinity of the values of g times the probabilities. As for the discrete case, the expectation operator has the following properties. The expectation of a constant is that constant, and the expectation operator is linear. We give here just one example of a computation of an expectation for a continuous random variable. Suppose that x is exponentially distributed with parameter lambda, i.e. that the PDF of x is given by lambda times e to the minus lambda x for x greater or equal to 0. The PDF is 0 for x less than 0. In that case, you can verify, using integration by parts, that the expected value of x, by definition is this integral, amounts to 1 over lambda. Now recall that we have spoken before about the relationship between a Poisson random variable and an exponential random variable. For a Poisson random variable with parameter lambda, the expected number of events per unit time is lambda. This means that you would expect to have to wait approximately equal to 1 over lambda between events. And that's precisely what this statement over here says. We will defer the computation of expectations for other common continuous distributions until we have another tool at our disposal, namely the tool of moment generating functions.